Welcome to all. In this video lecture, we will see multimedia compression and communication. This is the syllabus for Unit 4. In this unit, we will see from the first topic to random early detection. In this video, only the first part, that is from the first of the from the first topic to random early detection. Okay. We will see the topic. First of all, we will see the quality of service. In multimedia system consists of set of services. To provide generic multimedia services, services get parameterized, so called as the quality of service. Examples of quality of service parameters. Quality of service for audio services. Sampling rate is, for example, sampling rate 8000 samples per second, and sample resolution 8 bits per sample. Quality of service for network service. That parameters throughput is 100 Mbps and connection setup time is 50 milliseconds. Next, we see the quality of service concept comes from networking service and was introduced for specification how good the offered network services are. Services are performed on different objects. One is media sources, media sinks, and connections. And quality of service specification characterizes the service objects. Next, we see the different types of layers in the layer model of quality of service. This is the structure of the layer model. The first layer is a user layer, and that is, you can also say perceptual QoS, and second application layer. Third one is system, that is operating and communications layer. So this one it is go for device or network. So device means that is multimedia device, or through network we can communicate some other devices. So these are the layered model for quality of service. Next, applications of quality of service parameters. There are many parameters are there. From the applications of quality of service, you can mainly it can be classified to, that is, media qualities and media relations. That is, media qualities are divided intra-frame and inter-frame. From the intra-frame, component specifications are that is parameters, name, size, rate, importance, loss rate. And from inter-frame, media characterized, and there is parameters are sample size, sample rate, compressions. And the transmission characteristics parameters are end-to-end delay, sample loss rate, importance, and cost. These are the parameters of media qualities. Next, media relations parameters: synchronization, queue, integration, communication, conversions. These are the parameters of applications of quality of service. Okay, next we see system quality of service parameters. System quality of service parameters mainly divided into two systems, that is, two subsystem: application subsystem and network subsystem. From this application subsystem, there are three types: task per medium specification, task schedulers, and space requirement. From the task per medium specification parameters, priority, duration, period. And from the task scheduler parameters are task ordering, task begin, task deadline. And similarly, network subsystem, the task per connection specification parameters, priority, duration, and period. Similarly, task scheduler, task ordering, task begin, task deadline. and finally the space requirement. These are all the parameters of system quality of service. Next, network quality of service parameters. These are all network quality of service parameters. That is, it can be mainly divided three types: throughput specification, traffic specification, performance specification. That is, from this parameters: connections ID, packet size, throughput, burstness, and traffic parameters: packet loss rate, intermediate delay, packet end-to-end delay, and similarly performance spec. For performance spec parameters: ordering, error control, fragment or reassembly, communication type, cost, and periodicity. These are all network quality of service parameters. Next, deterministic quality of service parameters. That is, mainly it can be divided single value and pair value. That is, single value is QAS1. That are all average average QoS, and contractual value, threshold value, target value. Similarly, pair values are QS1 and QS2. That is, QS1 means the required value, and QoS2 is desired value. These are all examples and diagrams for the deterministic QoS parameters. Okay. And next, deterministic parameters values are given. That is, triple values. That is, QS1 is best value, QS2 is the average value, QoS3 is worst value. These are all examples. Some examples are given. That is, QoS is a network bandwidth. Okay. Next, guaranteed QoS. Guaranteed QoS. We need to provide 100% guarantees for QoS values are very close to 100%. That we call soft guarantees. Okay. Next, current quality of service calculation and resource allocation are based on hard upper bounds for imposed workloads, and worst case assumptions about system behavior. There are advantages and disadvantages are there. Advantages of QoS guarantees are satisfied even in the worst case, high reliability in guarantees. And disadvantage is over reservation of resources, hence needless injections of records. These are all advantages and disadvantages of the guaranteed QoS. Next, best effort of quality of service. No QoS bounds are possible. Very weak QoS bounds. There is advantages of best effort QoS is resource capability can be statically multiplexed, so hence more processing requests can be granted. There is disadvantages of best effort QoS is QoS may be temporarily violated. So these are all advantages and disadvantages of best effort QoS. Next, quality aware service model. Quality aware automation single service that consists of set of functions. There is here some set of functions are given, and some examples are given for quality aware automation single service model. Okay. This is a quality aware composite model. Last video, quality aware automation single service. This is a quality aware composite service that consists of set of automation services that are connected into a cyclic graph called service graph. These are all some examples are given detailed. We will see in later. Next, scheduling and policing mechanisms. Scheduling. Scheduling means choose next packet to send on link. Scheduling means choose a next packet to send on link. That is a transport link. The allocate link capacity and output queue buffers to each connections are connections aggregated into classes. Okay, scheduling next before, that is first in first out scheduling. Another one kind of scheduling, that is first in first out scheduling. It is based on the principle first in first out. So which is get into first, it goes to out first. That is sent in order of arrival to queue. So send in order of arrival to queue. Discard policy. If packet arrives to full queue, who to discard? Okay, here you see the trail drop arriving packet, priority drop or remove on priority basis, random drop or remove randomly. So this type of dropping policies are in scheduling mechanism. Okay, the structure shows the first in first out scheduling type. That is first in packet gets first out. That figure shows here. Next we see the need for scheduling discipline. Why do we need a non-trivial scheduling discipline? And that is for connection delay, bandwidth and losses are determined by the scheduling discipline. Okay, and then any can allocate different mean delays to different connections by its choice of service order. It can allocate different bandwidths to connections by serving at least a certain number of packets from a particular connection in a given time interval. Finally, it can allot different loss rates to connections by giving the more or fewer buffers. So these are all need for scheduling discipline. Next, first in first out, we will see detailed in first out scheduling. The disadvantage with strict first in first out scheduling is that the scheduler cannot differentiate among connections. It cannot be explicitly allocate some connections lower mean delays than others. A more sophisticated scheduling discipline can achieve this objective, but at a cost. The conservation law. The sum of mean queuing delays received by the set of multiplexed connections weighted by their fair share of the link's load is independent of the scheduling discipline. This is the conservation law. That is, the sum of mean queuing delays received by the set of multiplexed connections and weighted by their fair share of the link's load is independent of the scheduling discipline. Okay, these are the conservation law. Next we see the requirements for a scheduling discipline. A scheduling discipline must be satisfy the following requirements. So uses of implementation: pick a pocket every few microseconds. A scheduler that takes 1 0, that is O1, and not to on, that is n times. Okay, fairness and productions for best effort connections. FIFO, that is first in first out, does not offer any productions because a misbehaving connection can increase the mean delay of all other connections. Round robin scheduling. Okay. The performance bounds. Deterministic or statistical. The common performance parameters are bandwidth, delay, uh, there is a delay jitter loss. Easy and efficiency of admission control. To decide given the current set of connections and the descriptor for a new connection, whether it is possible to meet the new connection performance bounds without jeopardizing the performance of existing connections. Designing a scheduling discipline. Four principal degrees of freedom. There are the number of priority levels, whether each level is work conserving or non-conserving, the degree of aggregation of connection within a level, several order within a level. Each feature comes at some cost. For a small LAN switch, a small priority FCFH scheduler or at most two priority schedulers may be sufficient. For a highly loaded wide area public switch with possibly non-cooperative users, a more sophisticated scheduling discipline may be required. Priority scheduling. This figure shows the priority scheduling. The transmit highest priority queued packet is shown in figure. Multiple classes with different priorities. Class may be dependent upon marking or other header information. Example, IP source or IP destination, port numbers, etc. Depending on the marking, the priority is scheduled. The figure shows the priority. Next, priority scheduling. The scheduler serves a packet from priority level K only if there are no packets awaiting service in levels K plus 1, K plus 2, etc. up to N. At least 3 levels of priority in an integrated service network. Starvation, appropriate admission control and policy to restrict service rates from all but the lowest priority level. These are all priority scheduling. Next, round robin scheduling. This is multiple classes, cyclically scan class queues. This is a cyclically scan class queue serving one from each class if available. Provides protection against the misbehaving sources. Also guarantees a minimum bandwidth to every connection. This figure shows the round robin scheduling. Weighted fair queuing. Generalized round robin offers differential service to each connection or classes. Each class gets weighted amount of service in each cycle. This is the weighted fair queuing. Next, policing mechanism. Goal: limit traffic to not exceed declared parameters. Three common used categories that are all long-term peak rate and burst size. That is long-term. Otherwise, you can call average rate. How many packets can be sent per unit time? How many? That is average rate means how many packets can be sent per unit time in the long run. Crucial question, that is what is the interval length? That is 100 packets per second or 6000 packets per minute has the same average. 100 packets per second or 6000 packets per minute has same average. peak rate. Example, 6,000 packets per minute, packets per minute average, that is 1,500 packets per minute peak rate. Burst size, maximum number of packets sent consecutively with no intervening ADL. These are the policy mechanism of next. Finally, random variable detection. The random variable detection provides a congestion avoided by controlling the queue size at multimedia network. Random early detection notifies the source before the congestion actually happens rather than wait till it actually occurs. And next, random variable randomly early detection provides a mechanism for the gateway to provide some feedback to the source on congestion status. Random early detection algorithms show some parameters, that is minimum queue threshold, maximum queue threshold, average queue length, the maximum drop probability. These are all random early detection parameters. Okay. For each incoming packet, there is if average. This is for example for random early detection algorithm. Or on random early detection, there is function of average queue length is small burst go to untouched and effects of long lows. And finally, misbehaving users can be identified and severely penalized. Cooperating users get overall delays. Other issues with random early detection, fine-tuning minimum queue and maximum queue, maximum pair therapy, and weight needed for optimum performance. That random early detection needs to be deployed at the edge of the network. That's all about the Unit 4 first part. Thank you.